I love giving this presentation to RITSEC. It's an honor of mine. It's a privilege. So this is the first time it's going to be a little bit different in the infrastructure of Zoom. Those of you that have seen this presentation in the past, I have something that I usually do that I can't do during Zoom during this presentation, but I have a plan B for that. So stay tuned for that if you know what I'm talking about. All right. Without further ado, let's take a look at our agenda. We're going to talk for about 40 minutes or so about everything that will get you started in your education related to networking. You can use this particular presentation as your base to launch into many different areas and sub-disciplines related to a lot of the topics we're going to be talking about today. I always like to begin with a couple of funny stories. And usually I have funny stories at this presentation of something that happened over the summer, but we're on March 108th, 2020, so all the seasons and the months are sort of blending together. So I'm going to go back to last fall, and I'm going to tell you a funny story about a couple of funny stories that happened last fall. Starting with a bunch of families moving into the Brighton area where my family and I live. We liked some of those families, and we didn't like other families that moved into the area. We wanted to be friends with the ones that had kids the ages of our kids. So my wife made some care packages, some chocolates and fruits and wine and all sorts of goodies that she wanted me to give to these particular families that moved into the neighborhood. Not the ones that we didn't like, just the ones that we did like. So she gave me this care package. It was, I think it was on a Sunday night at 11:30, and she said, Jonathan, go ahead and deliver this package to the Smiths. And, I met that guy, Bob Smith, in Wegmans earlier that day. So he was on our Weissman approved list. But the problem was, since so many people and families had moved into the neighborhood, I wasn't quite sure which house was the one that the Smiths moved into. So on this Sunday evening at around 11:30 p.m., I took my amplifier, 500 watt amplifier, and a microphone, not this lovely Blue Yeti, but a musical instrument-oriented microphone, and I shouted, although I didn't have to shout, with the volume jacked up to 10 on a 500 watt amplifier. I said, Bob Smith, which house did you and your family move into? And as you might imagine, I woke up the whole neighborhood, including our kids. My wife spent a lot of time getting them to fall asleep, and she was like, Jonathan, what the hell are you doing? I'm like, well, you told me to deliver this package to the Smiths. I gotta find where Bob Smith is. And besides waking up our kids, I woke up a lot of kids in the neighborhood, and people were shouting, shut up, Weissman. They were throwing things at me. But you know what? I did get Bob Smith's attention, and he very discreetly walked over to my house and said, it's 123 Main Street, and then quickly ran back to his house because he didn't want to be associated with me because not too many people were happy with me at that moment in time. So later that night, like 11:45, maybe after midnight, I brought that package over to the Smiths. It wasn't quite finished yet. I put the final touches on it, and I brought it to the Smiths, and everything was fine. So that's a pretty cool story, right? That's story number one. Story number two. I'm originally from Staten Island, New York. If you haven't heard of Staten Island, New York, just think about the Impractical Jokers. They come from Staten Island, New York. So one trip, back when we were allowed to have fun and take trips and all that good stuff before COVID-19, we took a trip to my parents who are still in Staten Island, New York. And on the return trip back to Rochester, my wife and I and our kids were unpacking the bags from the trip. And one bag seemed inordinately heavy. I was like, what the heck is in this bag? And lo and behold, it was my mom's candlestick holders. And I immediately called the kids and I said, what the heck is this? And they said, you know what, they were pretty shiny and they look pretty good and they look good in our house. Like, you can't take grandma's candlesticks. They said, well, we thought we could. She said we could have anything we want. And then I checked my email later that night. I had like 5 emails from my mom. Do you see my candlesticks? Did you see my candlesticks? And I called her up and I said, look, I'll ship them UPS back the next day. And that's actually what I did. So what I had to do first was I had to Google for the nearest UPS store. and I found the nearest UPS store. I put the candlestick holders in a brown box. I brought it to the UPS store, and then that UPS store sent it to another UPS facility and another UPS facility and another UPS facility, and eventually it went to my parents' home back in Staten Island, New York. Pretty cool stories, right? All right, so oh, you wanted me to talk about networking today? Oh, I'm sorry. I thought you just wanted me to share interesting stories that happened. No, okay, so let's shift gears right now. Let's talk about networking right over here. Anytime a device, a node, wants to send traffic to a different device, a different node, the absolute first thing that happens in terms of the logic is the source of the traffic, or the soon-to-be source of the traffic, needs to determine whether the destination is on the same network or on a different network. If the source and the destination are on the same network, well, you know what? The source can deliver the traffic directly itself. It doesn't need any intermediary device. It can deliver the traffic directly itself. If the source determines that the eventual destination is on a different network, well, you know what? It can't deliver the traffic directly to the destination. It actually has to rely on some intermediary device. And some of the devices you'll encounter in the world of networking, in fact, the two most common devices you'll encounter in the world of networking, we've got a switch and we've got a router. A switch is a device that connects nodes or end stations or anything with an IP address, as we'll talk about in a little bit, of the same network together. Switches are like the local streets. You go from one part of the neighborhood to the next. Switches connect devices of the same network together. Routers don't really connect devices. Routers connect various networks together. Think of them as like the highways, where you can go from one highway to the next and then the next highway to the next highway. Routers are the connections between networks. Switches represent the connections within each individual network. Usually if I was giving this as a face-to-face presentation, although you do see my face, a body-to-body presentation, I would say, any questions or comments, but how you guys doing so far? John and everybody at Control Center, any comments or questions coming through so far?
None so far.
None so far. Let's keep going. Stop me at any point. In the world of networking, you cannot send any form of communication unless there are 4 different addresses listed in that actual transmission. 2 of them are known as IP addresses. IP stands for Internet Protocol, and these IP addresses can be described with these 4 characteristics that you see. They are logical. They are implemented through software. That's really what logical means in the sense. They are hierarchical, which means there's some form of levels that you can deduce what different parts of that IP address mean, coming up in a little bit. And really, most interestingly, they are geographical, which means looking at one of these things called IP addresses, in most cases, although not all, you can tell which part of the world and specifically which internet service provider that particular IP address comes from. So looking at our little illustration on the right over here, we've got an IP address, and visually we can say it's 4 base 10 numbers, IPv4 specifically today, 4 base 10 numbers separated by 3 dots, and that's why we call it dotted decimal notation. Decimal here meaning base 10, just like binary means base 2 and hexadecimal means base 16 and octal means base 8. Decimal here again means base 10, not that little dot. That's the dotted reference over here. So you got 4 numbers separated by 3 dots. That's an IP address. Of course, everything underneath the hood has some binary equivalent. Every number has a base 2 equivalent underneath the hood. And if you take a look over here, we've got the bits. We've got, in fact, 32 bits. Each one of those 4 base 10 numbers can be represented with 8 bits. The lowest number you can make with 8 bits, the lowest number you can make with any amount of bits is 0. The highest number that you can make with 8 bits, in other words, if all of these 8 bits right over here were 1s, that means the highest number you can get if you add up the column values, the 1s, the 2s, the 4s, the 8s, the 16s, the 32s, the 64s, the 128s, add up those numbers. What do you got quick? 255. So the numbers can theoretically range from 0 to 255, those 4 base 10 numbers of the IPv4 address, but there are some limitations and constraints. So it's not just as easy as saying it could go from 0 to 255. Looking at the IP address by itself tells you absolutely nothing. In other words, this hierarchy that I'm talking about, as applied to IP addresses, means that there are 2 parts of an IP address. The first part of the IP address is known as the network ID, the network identifier. That means every device, every node, every end station, whatever buzzword you want to use, on a network will always start off with the same bits. Simple as that. Just like everybody in the same zip code has the same zip code in a physical housing situation, and everybody in the same area code has the same 3-digit prefix on the phone. Well, it's the same concept, except we're not looking at the end for the zip code and an address. We're looking more like the beginning of the area code for the telephone, where you've got the first X amount of bits of that actual IP address representing the network ID. The second part of an IP address is known as the host bits, or the host section, or the host identifier. Again, there's so many different ways to permeate and change around the wording. So here's the obvious question now. Where is that delineation? Where do you know where the network ID ends and the host ID begins? Think of the host ID as like a serial number, a string of 1s and 0s that's unique to everybody on that network. You cannot have 2 devices, or God forbid more than 2 devices, with the same host ID, because then they can't be uniquely identified. Every device on a network will have the same network ID. That's what links them all together. The same string of initial bits. How many? We didn't talk about that just yet. But that host ID portion has got to be unique for all devices within the same network. Just like everybody in my area code has that same 3-digit prefix, and everybody in my zip code, 14618, has that same zip code. Well, you know what? You can't have 2 street addresses that are the same in 14618. And you can't have 2 telephone numbers that are the same in a certain area. So we need to obviously have a unique host ID portion. But again, where the heck do we break it up? Now, originally, when IPv4 addressing hit the world, and there's actually a date that I can give you, January 1st, 1983, that's known as Flag Day, where we turned off the old protocol system known as NCP, and we literally flipped the switch, and the world went to Vint Cerf's TCP/IP implementation. There is going to be no such Flag Day for IPv6. It's been a slow but rapid, lately, progression migrating around. Maybe I'll come back and tell you guys about IPv6, but today's presentation focuses on IPv4. Where is that breakup for the IPv4 address? Well, if you take a look at this handy dandy chart that we have right over here, there are different subnet masks, and that's the answer, by the way. That's the identifier in terms of how do we know where that network ID begins and where the host ID begins. Every IP address will also have a corresponding, as it's called, subnet mask. The purpose of a subnet mask is to uniquely identify the network ID, the shared bits by all devices on the same network. The subnet mask is also a 32-bit value. It's also written in dotted decimal notation. In fact, the acronym over here, you ever drink apple cider on a cold Rochester winter. Not that CIDR. It's classless internet domain routing. That's just a quick and dirty, funky way CIDR notation of representing the subnet mask. Before I talk about CIDR, let me talk about the dotted decimal notation of the subnet mask. If we have a subnet mask, let's just pick, where's my mouse? Let's just pick this one right over here. 255.255.0.0. If you take a look at the binary equivalent, 255, as we mentioned, consists of 8 ones. 255, as we mentioned, consists of 8 ones. 0 consists of 8 zeros, as we mentioned. If you take each one of these bits and line them up underneath the bits of an IP address, and you perform the logical AND process, which means bring down a 1 if you've got 2 ones in a column, bring down a 0 if you've got any other patterns, that will uniquely identify which bits are shared by every device on the network and which bits are unique in terms of a total string for the host ID on the network. Let's actually see how that works, and let's tie that into our stories so far. Let's say the source of traffic has an IP address of 10.0.0.1. And this guy, 10.0.0.1, wants to send traffic to 10.0.0.2. Remember what we said. You can't have an IP address by itself. You need a subnet mask. So in this case, the subnet mask is 255.0.0.0. So the black represents the IP address. The blue represents the subnet mask. It's the same, except it's a different numbering system. This is obviously base 10 over here. This is obviously base 2, binary, right over here. Remember, this is the 2's column and the 8's column. 2 plus 8 is 10. Excuse me, this is the 1's column, so that's going to give you a value of 1 for the last number in the IP address, known as an octet, because we've got 8 bits representing each of these numbers. So here's where the story continues. 10.0.0.1 takes his IP address and his subnet mask, lines up all the columns very neatly, and then he does what I was talking about. He does that logical AND process. Every column is going to have 2 digits. If both of those digits in the column are 1s, Boolean AND, we bring down a 1. Every other pattern, we bring down a 0. So as you can see, when we do that logical AND process with the IP address of 10.0.0.1 and the subnet mask of 255.0.0.0, there are only 2 columns in all those 32 columns that actually have 2 ones in them. It's the 2's column over here, and it's the 8's column over here. 2 plus 8 is 10. What shines through is an orange right over here. What's shining through is the network ID. So that lets the host know that it's on the 10.0.0.0 subnet. Anytime you've got a 1 bit in the subnet mask, that means the corresponding bit in the IP address is a network bit shared by every device on the network. Anytime you've got a 0 bit in the subnet mask, that means the corresponding bit is a host bit and part of this host identifier serial ID unique string that all devices have on a particular network. So every device on this network will start with 10. First octet will be 10. That's a guarantee. And another way we can describe this network addressing scheme in front of us right now is that the first octet is a network octet shared by all devices on the same network, whereas the last 3 octets are host octets and able to be assigned in totality uniquely to each device on the network. Okay, so the host knows what network he's on. Who cares? Well, the host cares, because the host has to now figure out whether he's on the same network as the destination or a different network. So what the host does is he takes the IP address of the destination. Well, how does a host get that destination IP address? Well, either he has it or he asks for it. Or more than likely, of course, there's going to be a phenomenal protocol you're going to be learning about called DNS, arguably my favorite protocol in the whole world, domain name system. DNS takes a name and throws a number in translation. In other words, you give me the FQDN, you give me the fully qualified domain name like www.rit.edu. I will give you the IP address that goes along with it. There's a lot more involved in DNS, but that's its major, well-known, renowned functionality. You give me the name, I give you the number. So getting the destination IP address at this point, let's say it's not going to be an issue for 10.0.0.1. 10.0.0.1 knows that he wants to communicate with 10.0.0.2. So he lines up those 32 bits of 10.0.0.2 in binary. And then the host is like, what the heck is the subnet mask of the destination? In fact, host has no idea. The host will actually, in the second logical AND process, use his own subnet mask. He says, my subnet mask, as it says here in my TCP IP configuration, my subnet mask is 255.0.0.0. So you know what? I don't need that destination mask. You know why? Because if the destination is on the same network as I am, the mask is going to be the same anyway. So the source of traffic will take the destination's IP address with, once again, the source subnet mask, line up those 32 bits, and once again perform the logical AND process. Again, a subnet mask of 255.0.0.0 means that everybody on this network will share the first 8 bits. One means it's a network bit. One means it's a network bit. Because this IP address starts off with 10 in the first octet, that's how we can conclude that every device on this network starts off with 10. Now, when you get the subnet masks that have numbers that look like this, 255.255.255.128, it becomes really an arduous task to say and even to type out in certain cases. CIDR notation says, just tell me how many network bits you have. What's easier to say? 255.255.255.128 or just /25? Obviously the latter. So /25 means that the first 25 bits by every device on that network are network bits and shared by every device on that network. The number of bits that are network bits does not have to be contained to a single octet, and clearly 25 doesn't. 25 means we got 8 here and 8 here and 8 here and 1 right over here. Network bits are always at the beginning. Host bits are always at the end. There's never any deviation from that pattern. So continuing our story, after that second logical AND process, the host comes up with a network ID of the destination that matches the network ID of the source. It's at that point when those two network IDs are the same that the source says that is local communication. I can deliver the traffic myself, and the source sends the message directly addressed to the destination without care and concern for any other intermediary devices. It goes transparently through the switch, but we don't need to get anybody else involved because the switch is transparent. The traffic goes in one interface, out the other interface. The switch doesn't touch or manipulate the traffic in any way. The switch just sends it through. So that is an example of local communication. In other words, the source delivered the traffic directly to the destination because the source realized the destination was on the same network. That sound familiar? About that time, I was out on my stoop at 11:30 on a Sunday night. I knew that Bob Smith and his family moved into a house that was in my network. So what did I want to do? I needed to get his attention. So I got his attention. And you're going to see how that works from the networking perspective in a second. But I delivered the traffic directly to Bob and his family. That's an example of local communication. But, look what happened over here. Now, 10.0.0.1 wants to talk to 11.0.0.2. After performing the two logical AND functions once again, source concludes again he is on the 10.0.0.0 network. That is always done. That stuff, like many networking functionality, is never cached. That's done on a one-by-one tit-for-tat basis. But right over here, the new destination 11002, when logically ended with the source subnet mask, gives you a network ID of 11000. And clearly it's the ones column over here in the first octet on the left that's differing from the previous version. So it's at this point that the source says, oh no, the destination's not on my network. I can't deliver it myself. I've got to get somebody else involved. And that somebody, as we'll see in a couple of minutes, is a device known as the router. That sounds like another story also, right? Oh yeah, remember when my kids took my parents' candlestick holders and I had to get it back to them, and I love going to Staten Island, and I missed Staten Island since the pandemic started. I haven't been there, but I wasn't going to drive all the way down to Staten Island again. I just drove 6 hours back to Rochester. So what I did was, I put it in a brown box, and I told the UPS people, I said, you guys deliver it. And that's what the source will do in this traffic. The source puts it in a brown box and says to its router, its UPS facility, go ahead, you deliver it. And we'll see how that works in a couple of seconds as well. So when, as we mentioned, you have a name, but you don't have a number, that's where DNS comes into play. But there's still a problem now. The problem is IP addresses are logical and geographical and software-based and hierarchical. And they change based on who's on the network at that time. Sort of like a uniform on a Major League Baseball team. One season, player X might be wearing number 52, and the next season, some player Y might be wearing number 52. Which device is in possession of a given IP address at any point in time? How can we keep track of that? How can we tie a logical IP address to a physical device, to a physical machine? Oh, this stuff might help us right over here. The network interface card and media access control address. Let's see what's going on over here. By the way, one of my biggest pet peeves is somebody would say, oh yeah, my NIC card. No, don't say NIC card. C stands for card. You go to the ATM machine, you enter your PIN number, so just call it NIC. So we got a NIC, which is a physical device. And by the way, for many years, it hasn't been a card. Of course, for many years, it's been a chip. I try to get industry to stop expanding the acronym from network interface card to network interface chip. And I guess just my students and I are the ones that are doing it. But network interface card is how we expand it. It's a device that's in a system allowing for the network communication. It's a transceiver. It transmits and receives signals. But you know what? When these NICs are made at factory, they have an actual address, a unique ID. And by the way, when I say unique, I'm not talking about the company. I'm talking about the entire world, the entire universe, the entire galaxy. Every NIC that's made has a unique MAC address. And compare some of these words to the words we saw on the IP address slide. It's not logical. These addresses are physical. It's not software. It's hardware. It's not hierarchical. It's flat. And it's not geographical. What that means is if you go to a website and you buy a NIC for whatever reason, you want an external NIC, of course, all devices come with them soldered on. You buy some external NIC, and somebody from California buys a NIC from the same website. You and that guy in California could very well wind up with sequential MAC addresses. In other words, there's none of this hierarchy with network ID, host ID, but the MAC address does consist of two parts as well. The first is known as the OUI, the Organizationally Unique Identifier. And that means that if you want to make a NIC, you're a company that wants to make a NIC, you've got to register with the IEEE organization to get a block, to get those first 6, and now we're not dealing with base 10, we're not dealing with base 2. Who knows what numbering scheme we're dealing with here? You got it. We're dealing with hexadecimal. So you got to register for that prefix, the OUI, which is a fancy way of saying the vendor ID. The vendor who made your NIC is going to be uniquely assigned a 6-digit prefix. Now, of course, companies that make lots of NICs have multiple OUIs. Even VMware, even hypervisors that implement virtual machines with virtual NICs, you can look at the MAC address assigned to your VM, and you can instantly know what hypervisor it is. Now, of course, MAC addresses can be spoofed and changed. Take a class with me. We'll talk about that another day. But no NIC will have the same MAC address as another NIC in the entire galaxy. The second part of the MAC address, there are different buzzwords. The UAA one that you see on the slide is not really the most well-known way of identifying it. Most people actually call this the block ID, and this part right over here, the device ID. It's a serial number, a unique 6-digit hexadecimal digit string that represents that unique NIC. In other words, if all the NICs made by a particular vendor start off with the same 6 hex digits, they can't have a duplication of that second 6 hex digit part. That's why no two MAC addresses or NICs in the entire world will ever have the same address, spoofing aside, past, present, or future. All right. So now let's see how the MAC address relates to the IP address. Remember, a little while ago, I said you can't send any form of network traffic unless you have 4 addresses. 2 of them are IP addresses, one for the source and one for the destination. And now 2 of them are MAC addresses, one for the source and one for the destination. The MAC address of a device is going to be bound or married to the IP address of a network. What that means is if you take your laptop to RIT, the RIT DHCP, you'll learn about that in another class, Dynamic Host Configuration Protocol, the RIT DHCP server, which gives you an IP address on the glorious 129.21.00/16 infrastructure. That IP address that you get at RIT will definitely start with 129.21, first 2 octets. It doesn't mean that it's a /16 mask. There's been some other breakup of the network ID, but we'll save that for another day. At home or at Starbucks or at some other location. Of course, if you're using your laptop at Starbucks, please make sure to use a VPN. That's the single worst thing you can ever do. Use public Wi-Fi without a VPN. We'll talk about that another time. But when you have your laptop at home, your DHCP server implemented in a box that we just call router is going to give your device a different network ID based on where you are geographically. There's a whole thing about private and public IP addressing that I'm not going to get into today. Just giving you some food to think about as we go through this presentation right over here. My point is your MAC address never changes. Your MAC address is the same whether you're at RIT or Starbucks or Dunkin' or wherever you are in the world. Your MAC address will always be the same because it's burned into that actual chip. BIA, burned in address, whereas the IP address will vary by the network that you're connected to. So the obvious question is, on a network that has a particular IP address, well, which device is now bound? Which MAC address is now bound to that IP address? So here's what I call a little scoreboard. This is the source of traffic saying, look, I got to fill in these 4 addresses in order to send traffic to the destination. Source says, I know my IP address is 10.0.0.1. I know the destination IP address is 10.0.0.2. I know that my MAC address is all A's. How does the source know its MAC address? Well, it's built into that device itself. It just reads it off that chip. Now, of course, these NICs might come with stickers and labels that have your MAC address, but that's not how the configuration actually works. It's burned into the actual chips, or if you have an expansion card, burned into the cards. But the source will never know what that destination MAC address is right off the bat. How the heck would it know that? So this is where you have to start planning for your future. Do you ever see those commercials for AARP late at night? Oh yeah, you get these AARP cards in the mail. Actually, I have one in my wallet that I show students. Not that I'm necessarily that old, but I just put my finger over the first day because one of the most important networking protocols is ARP, Address Resolution Protocol. And here's how it works. The source says to himself, look, I got to send traffic to 10.0.0.2. I know he's on my network. I just don't know which device has control over that IP address right now. So what the host does, what the source of traffic does, is he takes a 500-watt amplifier and a microphone and screams into it in the middle of the night, interrupting everybody, bothering everybody. But you know what? He did get the attention of the actual destination. I got Bob Smith's attention. Host A sends a network broadcast in the form of what we call an Arp request. And what an Arp request is, it's a network broadcast that gets literally every device on the network to stop what they're doing and see if the IP address and the ARP address in the ARP request is theirs. In other words, a source will say, if your IP address is 10.0.0.2, give me your MAC address. So everybody in this little diagram, let's pretend host B is 10.0.0.2. Host C is like, shut up. Host D is like, look, I'm doing important things. Stop interrupting me. I just wasted all this time right over here. But host B says, ooh, that's for me. And sends an ARP reply back to host A. Now, the ARP request is a broadcast, which means everybody in the network's got to stop what they're doing and focus on that broadcast. The ARP reply is what we call a unicast. Unicast means there's one source and one destination. We'll see how that works through the switch in a little bit. But host B's response, ARP reply, back to host A, doesn't bother host C, host D, or any of the other devices on the network that are not being pictured right over here. You know, that's like when Bob Smith saw that I made a fool out of myself and woke everybody up and didn't endear myself too much to everybody in Brighton. Bob Smith wasn't going to shout out, hey, Weissman, it's 123 Main Street. Bob Smith very, very quietly, very stealthily walked over to my house. That's a unicast. That's local communication. And by the way, that answer to Bob Smith's question, host B says my MAC address is BBBB, and now the source has everything it needs to send traffic to the destination and fires it off. So let's see how that works within a switch. If you take a look at our little diagram right over here, we have two switches that are interconnected together. Fred and Barney are connected to switch 1, and Wilma and Betty are connected to switch 2. When the switch is powered on, this device knows nothing. It's blank. So let's say Fred is 10.0.0.1 and Barney is 10.0.0.2. So Fred is going to start off with his ARP request, which is going to go into the switch. Switches take broadcasts and flood them out of all ports except the port on which the message came in on. So the switch will send the message to Barney and to this switch, which will send it to Wilma and Betty. Everybody's interrupted. But as soon as Fred sends his message into the switch, his MAC address, and this is the MAC address right over here. Cisco, by the way, represents MAC addresses a little bit different than the rest of the world. Cisco represents MAC addresses with 3 hex digits, 3 pairs of 4 hex digits separated by dots. The rest of the world usually does 2 hex digits and a delimited character. So anyway, we got 12 hex digits right over here. That's Fred's MAC address. As soon as Fred sends a frame into interface F01, fast Ethernet 0/1, you'll learn about that in a different class, into switch 1 right over here, look what happens. The switch says, oh, I know what device is connected to F01. And the switch adds the MAC address of Fred to its cache of MAC addresses that it's collecting, associating with ports. So the switch clearly knows where this address is. Since this is a broadcast, the switch sends it to every device right over here. So Barney and Betty and Wilma, they all get that ARP request. And the ARP request says, if your IP address is 10.0.0.2, send me your MAC address. So Wilma's like, I'm not 10.0.0.2. Betty's like, I'm not 10.0.0.2. Barney's like, oh, I am 10.0.0.2. So Barney sends an ARP reply. But in the ARP request, Fred said, this is my IP address, this is my MAC address. So Barney doesn't need to interrupt everybody himself and say, hey, if your IP address is, Barney's got only information he needs. So Barney sends the traffic in a unicast fashion. In other words, it's going to have a destination MAC address of Fred right over here, and that ARP reply goes back into the switch. The switch says, do I know where that MAC address is? And the switch now looks at its table in RAM. This is either known as, in the world of Cisco, as a MAC address table. In other circles, it's called CAM, Content Addressable Memory. Generically, it's known as SAT, Source Address Table, because the switch learns where devices are by them sending traffic. So because the switch knows where Fred is, the ARP reply only goes out of interface F01 and does not bother anybody else on the network. That's why unicasting is so much better than broadcasting. Now, after Fred has Barney's MAC address, now Fred can send the regular traffic, and it's like a virtual circuit is created within the switch, and the traffic does not go to any other device. Eventually, you'll take a look at these populated SATs on each of switch 1 and switch 2. After Fred and Barney and Wilma and Betty have all sent traffic, as far as switch 1 goes, Fred and Barney are accessible on ports F01 and F02 respectively. By the way, the A stands for, is the second letter in the fast. Here, you don't have the A over here. It's the same interface. But what about Wilma and Betty over here? When Wilma and Betty send traffic into switch 2, and it's a form of a broadcast traffic, the Gigabit Ethernet 0/2 interface will send it right into switch 1. So when Wilma and Betty send traffic, and switch 2 sends that traffic out of the GIG02 interface, it goes into switch 1 on the GIG01 interface. And that's why Wilma and Betty and any other device not in switch 1 will be in the SAT of switch 1. Look at this, associated with that GIG01 interface as if they were directly connected to that port. And it works the same way in reverse. In other words, Fred and Barney, if you take a look, are learned on switch 2 when their traffic enters the GIG02 interface right over here, and that's what switch 2 thinks that Fred and Barney are directly connected to. Now, with this infrastructure, Wilma is known on interface 3 and Betty is known on interface 4 of switch 2. So the switches are doing some learning as the traffic is being sent, and that's how the MAC addresses and the IP addresses can work together for local communication. This is all one network. You don't have a router, you only have one network right over here. Okay. When the traffic goes into the switch adds your MAC address and associates your MAC address with the interface on which that MAC address was heard. And as a result, the switch doesn't have to send any broadcasts or any unknown unicast, I should say, which is treated like a broadcast if the switch doesn't know where destination MAC address is, and it's a unicast piece of traffic, the switch will just send it out of all ports like it was a broadcast. This learning process makes it much better to cut down on the flooding of traffic, interrupting people that don't want to hear the message. That's the same thing. We're running a little bit low on time, so I'm just going to go right now to remote communication. Ooh, look at this infrastructure right over here. Let's say we've got these networks. You got the 12.0.0.0/8 network, the 11.0.0.0/8 network, the 14.0.0/8 network. Of course, see these links over here between router 1 and router 2, and these links. Every link represents a separate network. These are just like backbone networks. There's no end stations. There's no population of end stations on these networks. They're just the highway interconnections from one highway to the next. You can take the thruway to 490 or 390. So if you take a look right over here, let's pretend the source IP address comes from this network here, 12.0.0.0/8, which, and /8 means the first octet is a network octet shared by every device on the network, and the last 24 bits are the host ID. So the source of 12.0.0.1 wants to send traffic to the destination of 14.0.0.1. After performing the logical end process, the source says, oh, I know, the destination is on a different network. I need help. You can't send traffic to a node on a different network directly. You need to send traffic to your default gateway, which is the IP address assigned to the interface of a router connected to your network right over here. And that's going to be part of the configuration that all hosts will have. If you're not configured with a default gateway, you are never sending traffic off your network. So here's what happens. The source knows its IP address. The source knows the destination IP address. This guy right up here will call 14.0.0.1. Source, of course, knows what his MAC address is. But wait a minute, I'm one ahead over there. The source doesn't know what the destination MAC address is. So once again, it's ARP time, Address Resolution Protocol. The source will interrupt everybody on this network. And by the way, the broadcasts hit the router interfaces, but the routers will never, they never have, they never do, and they never will forward broadcasts. Imagine a router forwarded a network broadcast and it went all around the world and back. That would obviously be very degrading for the bandwidth of the internet infrastructure. Routers never, ever forward broadcasts. Switches always do. So let's say the source right over here, 12.0.0.1, wants to send traffic to the destination over here, 14.0.0.1. Another ARP request is sent, but now instead of saying, hey, 14.0.0.1, what's your MAC address? That can't happen. Can't happen because 14.0.0.1 will never hear that ARP request. The broadcast never gets past this point right over here. What the source actually does is he says, hey, if your IP address is, and now he actually doesn't have 14.0.0.1, he has his default gateway's IP address. Let's call it 12.0.0.99. If your IP address is 12.0.0.99, I need your MAC address. All these devices say, oh, shut up, you're wasting my time. The router interface says, ooh, that's my IP address. I'll send an ARP reply back. And the router says, my MAC address is BB. We're using shortened versions of MAC addresses right now for space purposes. So host says, okay, let's send the traffic now. And the PC here sends traffic through the switch. It hits the router interface. The router interface says, let me look at that destination MAC address. Yep, that's mine. Let me look at the destination IP address. That's not mine. But the routers have, as you see here, these handy dandy tables in RAM. Like the switch had its table, there's a different table that the routers have in RAM called, get this, a routing table. And the routing table consists of networks and how to get there. So router 2 gets the traffic. He says, oh, it's for me because the MAC address matches. But since it's not my IP address, let me do my due diligence and let me get this piece of traffic on its way to the destination. Do I know about that network? And the router says, oh, yeah, look, I got a beautiful entry right over here. 14.0.0.0/8 matches the network ID of this destination IP address here. So the R2 guy says to himself, who do I send it to? So this router says to get to the, I'm sorry, it's this is the routing table of R2. Got to align ourselves a little bit better. This is the routing table of R2 over here. So router 2's routing table says to get to the 14 network, I need to send it to R1. Here's R1. But wait a minute now. R2 just can't send that message to R1. Why not? Because R2 doesn't know what the MAC address of this interface is, assuming everything is an Ethernet interface in this little story right over here. So coming out of the interface here of R2, destined for everybody in this network, which just might be this interface over here, R2 will send an ARP request that says if your IP address is, and lists the IP address of this router interface, I need your MAC address. An ARP reply comes back, and watch this now. Bam! There's a new source MAC address, that's this interface. There's a new destination MAC address, that's this interface. And R2 sends the original traffic sent by this host. R1 has that same situation. He says, that's my MAC address, but that ain't my IP address. Do I know how to get to the 14 network? And now this is the match over here as far as our story goes. Router 1 says, I know how to get to that 14 network. I got to send it to this guy right over here. But I need the MAC address. So out of this interface of R1 will be an ARP request. R4, when he gets it on this interface, will send an ARP reply back. And once again, we're going to cross out MAC addresses. And now the new source MAC address is EE, And the new destination, kind of shortened version of a MAC address, is going to be FF. R4, once again, that's my MAC address, but that's not my IP address. R4 looks in his routing table and sees that he's directly connected to the 14.0.0/8 network. And he says, I can deliver this directly, but I'm going to need the MAC address of the actual destination. So one more ARP request and ARP reply, but the ARP request sent by R4 is actually heard by all the devices on that network, and the destination sends an ARP reply back in a unicast fashion. And now, one more time, new source MAC address, the G's, and new destination MAC address, the H's. This Nick over here says, that's my MAC address. And for the first time in the story, that's my IP address as well. And now the message is read and understood. So I didn't want to drive all the way back to Staten Island. I had to look up my nearest UPS store on Elmwood Avenue it was. So that's like me bringing the brown box to UPS right over here, that Google search to find out where my nearest UPS store was. I went home. I didn't care about anything else. It was in good hands. But my UPS store in Brighton didn't deliver the message, the brown box with the candlestick holders, to my parents in Staten Island over here. R2 found the next UPS facility. R1 found the next UPS facility. And that's how internet routing works, where the sender of traffic just cares about getting to its gateway. And that router only cares about getting it to the next stop. And that stop only cares about getting to the next stop. And it's a piece-by-piece journey until the transmission actually reaches the destination. And as you see with this beautiful illustration, every time traffic moves from one network to the next, the outer encapsulating layer known as a frame is stripped off. And that's where the source and destination MAC addresses are. And there's a new frame that engulfs the packet and everything inside of the packet that's being sent with the new MAC addresses. Think about a UPS box that you're tracking, and you got these stickers that are slapped on when you move from one facility to the next. Same thing, except instead of slapping on those stickers, we're stripping off the frames and we're placing the frames with new frames. Every time you scan in and scan out, it's a trackable UPS package. Every time a packet moves from one network to the next, it's going to have a new source and destination MAC address. But of course, me here in Rochester and my parents in Staten Island, the actual endpoints in the communication, and in our story, they would be the source IP address and destination IP address. Those never change. So you see, you can't have one without the other. You need the logical IP addresses, of course, to represent positions within a network, but now you need the MAC addresses to represent the devices that are currently using those corresponding IP addresses. You want another example of what I said? In order for traffic to reach the destination, you got to have the MAC addresses that represent the hop-by-hop progression across the routers. But the IP addresses, those can't ever change. So MAC addresses and IP addresses, yeah, can't have one without the other. The physical way in and out of machine for network traffic is the NIC, as we've seen. It's a transceiver, transmits and receives signals. But the logical way in and out of machine is through a program. In other words, okay, the ones and the zeros are coming into the NIC. Now what? The logical way in and out of machine is through a program. Anytime you hear the word program, you know, you're thinking of the word application, or you're thinking of the word software. What it really means is it's lines of code that follow algorithms to solve problems or accomplish tasks. That's what a program is. A program that runs in the background, independent of a logon, is a service. In the world of Linux, we don't call them services, we call them daemons. But Linux has a term called service. And that's basically a command that calls the scripts which control the daemon processes. And I want to talk about those a couple of words before we continue our story. A process is an instantiation of a program when it's actually invoked and it's running in memory. And the smallest execution of a program, smallest traceable execution line, is a thread. All right, we're almost out of time, so I want to get right to the grand finale over here. We said, okay, the physical way, those bits, whether it's electrical bits on a copper-based NIC or fiber bits, light representing ones and zeros on a fiber NIC. Clearly, that's the physical way in and out. But you know what? As we said, the logical way in and out is through this thing called a program or a service. Okay, so how the hell do you get into a program or service? And that's through this thing called a port, which is a logical endpoint represented by a number. So these two folks live in an apartment building together, 500 Bob Street, Anytown, USA, 12345. You want to write them a letter, it's the same address. But that guy, his name is Frank Thomas Peters. He lives in apartment number 21. And that lady, Helen Teresa Thomasina Parker, she lives in apartment 80. If you want him to get the letter, you say apartment 80 on the envelope. If you want her to get the letter, did I say 80? You want him to get the letter. Remember, he's Frank F. Thomas T. Peters. That's 21 FTP. And she is Helen Teresa Thomasina Parker, HTTP. She lives in apartment 80. So for him, it's apartment 21. For her, it's apartment 80. And that's exactly how your machine works. When you get traffic into a machine physically through the NIC, let's say the machine is running both an FTP, file transfer protocol server, and an HTTP, hypertext transfer protocol, unencrypted web server. Well, you know what? That's where another form of addressing known as port numbers comes into play. The port number will specify which program or service the message comes from, source port, and which program or service the message is destined for, destination port. So if you've got an FTP server running on the same machine as a web server, they both are accessible by the same MAC address, the same IP address. How does Frank get his mail, and how does Helen get her mail? How does the FTP server get the FTP traffic and the web server get the HTTP traffic? That's the port number. That's how you identify unique programs or services and take messages from them and deliver messages to them. That's port numbers. Port numbers come in three categories. Server services are going to be in this first category, the well-known port numbers. So when you're talking about DNS, think about 53. When you're thinking about DHCP, 67. That's the only port, by the way, when we last left you, we were talking about open ports and closed ports and filtered ports, but just to bridge the two parts of today's presentation, an open port is a port that has a program or a service listening for incoming communications. A closed port does not have an associated program or service listening. That's it. When you want to open a port, you start a service or program. When you want to close a port, you stop a service or program. Firewalls don't open ports. Firewalls don't close ports. I think I was somewhere in this little story, so I'll just start that story again. I do a lot of consulting, and I see people out there in industry that don't know too much about what they're talking about. So one time, a guy asked me to close up port 22. He didn't want anybody to SSH into his infrastructure from the outside. He said, Weissman, can you close up port 22 on my firewall? I said, no. He said, what do you mean? No, I thought you knew your stuff. No, I can't. He goes, no, come on, stop being funny. Go ahead and close up port 22. I said, I can't close up port 22. Port 22 is open on your SSH server. That's a service that you've started on that machine. I can't close it up from the firewall. I could write a rule that filters, which means blocks, traffic on the firewall from entering your infrastructure if it has a destination port of 22, but I can't just close port 22 on your firewall because port 22 is not open on your firewall. He's like, what? So I said, okay, I'll close port 22 on your firewall. So firewalls don't open ports. Firewalls don't close ports. Firewalls filter ports. Filter means to block. They let certain traffic in and they don't let certain traffic in. They let certain traffic out and they don't let certain traffic out. 1 second, let me just get my mouse. There we go. Now, this layer 4 information that we're talking about, this port number information, that's found in something that we either refer to as a TCP, Transmission Control Protocol segment, or a UDP, User Datagram Protocol datagram. So don't say TCP packet, don't say UDP packet. It's a TCP segment or a UDP datagram. Like the IP packets keep the source and destination IP addresses. Like the frames keep the source and destination MAC addresses. So one of my final questions here today is, when would you use TCP and when would you use UDP? First off, TCP is where integrity is of utmost importance. If one bit gets corrupted, either accidentally or maliciously, the whole message can change or just be completely unreadable. So when you're dealing with file transfers, when you're dealing with websites, when you're dealing with SSH, when you're dealing with data that needs to be reliably received, TCP has a lot of additional functionality that slows down the connection with additional headers and in the header, additional fields and values, and a whole process known as a three-way handshake. I'm going to show you in a second, but point is that it's significantly slower than if its cousin UDP was being used. Web browsing, another great example for TCP. UDP is where you put a stamp on an envelope and you mail the letter. If it gets there, it gets there. If it doesn't get there, it doesn't get there. You have no idea if it got lost. Person you sent the letter to has no idea that you actually sent them a letter. So TCP, look at that green chart over here. It's reliable. UDP is unreliable. Up until less than 30 minutes ago, up until 15 minutes ago, I always used to say, hey, they lied to you. Everybody always says that there are two things that are guaranteed in life. What are the two things that are guaranteed in life? Death and taxes. And I always used to say, well, you know what? There are actually three things that are guaranteed in life. There's death, there's taxes, and there's TCP. In other words, if TCP is being used, there is a 100% guarantee, and I'm saying it's even higher than reliable. It's a 100% guarantee right up there with death and taxes that the messages will get delivered, and if there's a problem, they're going to be resent. In fact, when you think about Twitch and you think about YouTube and you think about all these sites that we quote unquote stream from, it makes sense that if TCP takes some time, as you see, to establish a connection, sort of like taxiing an airplane does before taking off, and UDP, you just send it off. TCP has this, let me just show you right here, this thing called a TCP Three-Way Handshake, Cincinnati. You'll learn about that in another class. You got all this additional overhead to make sure that the messages that are sent are received, and if not, they're resent again. So TCP is guaranteed, UDP is not. TCP is connection-oriented, and an actual connection is established between the sending and receiving machines. TCP deals with these things called acknowledgements, which means every time you get some TCP segment, you, the destination, have to say back, I got it. And if you don't say, I got it, the source will assume you didn't get it and send it again. That's how TCP is 100% guaranteed. So TCP, when you think about going to websites, email, FTP, SSH, that's where reliability is more important than speed. Integrity is more important than speed. But with UDP, with voice over IP, and certain types, as you see over here, of music streaming, or you're talking to an important server in your network. When you query your DNS server, your DHCP server, they use UDP. There's one small thing called a zone transfer that is going to be TCP on DNS, but you'll learn about that in a different class. But for the most part, these major infrastructure servers, DNS and DHCP is always UDP, because you know what? I always say this to my students: if you're in a class and you ask the professor a question and the professor doesn't answer you, just ask that question again. You'll never have that problem in one of my classes, because I love questions. So UDP is fast because there are not that many fields. There's no additional overhead of establishing a connection and maintaining the connection. There's no need for sequencing or for ordering. None of that applies to UDP. Again, it's like the stamp on the envelope and you put it in the mailbox. With TCP, though, there's this three-way handshake at the beginning, and then we've got sequencing. We're counting the bytes. We're ordering the bytes. If bytes come out of order, they're rearranged, but if we're missing bytes, we say, I'm missing these bytes right over here. It's significantly slower, but you know what? It's a trade-off. For those applications that are going to actually make the decision on which one of these to use, TCP is the protocol of choice for those applications. But when you're dealing with VoIP and you're dealing with certain types of streaming and DNS, aside from a zone transfer, and DHCP, which always uses UDP, that's where speed is the most important thing. I don't care if my server didn't get that message. I'm just going to send it again. If your professor doesn't answer your question, you ask the professor again. So what sounds better? What's better, TCP or UDP? I got the chat box on Twitch open up, so somebody type in which is better, TCP or UDP. Nobody wants to type it in? Oh. Okay, those answers over there, people who have had me as a professor have seen this presentation again, or maybe you're just right on the money with where I'm going with this. Sometimes somebody will say, oh, it's TCP, oh, you got this great reliability. And sometimes people will say it's UDP because you got the speed. And I would say to those students, well, what are you going to wear when you're 90? Answer that question in the chat box. What are you going to wear when you're 90? Yes, you got it. Neon Spandex. I guess the username is right on the money with this one. The answer is depends. So what is better, TCP or UDP? The answer is it depends, obviously, on the actual application that is using this. So far, so good. Now, I did want to do something I've always done during these Weissman-Ritzek annual networking presentations that I'm just not able to do today. So instead of not doing it at all, hey, fan 5152, shh. So instead of doing that in a simulated way, I want to show you a video of this point in the presentation last year. Same slide. Watch this. And that hello message back again, and they're going to be getting duplicate messages. So for all those reasons, it makes sense where speed is of the essence to use UDP, and where integrity is of the essence to use TCP. So far, so good? What's your name, by the way? Jess? Don't go so far. Oh, sorry. So that's an example of UDP, where he doesn't know that I sent him those markers, and I don't know that he got the markers, and I just send it, and it was very quick. There was not a lot of overhead, but I got the message. Hopefully I got some of the message to him. If the messages didn't reach him, then you know what? I don't care. I'll just send it again. And that's why I would be firing markers all day long if I needed to, until I got a reply from him. That's UDP. I think I might have more. Hang on. I got to show you with TCP. Yeah, please, if you can. Uh-oh. Okay. Okay. All I need is two. Let's do TCP now. Adriana, can I bother you for a second? Hi, Adriana. I'm Jonathan. Can I send you some markers? Say I got the blue marker. She got the blue marker. Yes. She got the red marker. Yeah. She didn't tell me that she got the black marker. I have a copy of it in RAM, by the way. Not timer expired. Let me send her that same copy. That's TCP. The additional overhead, the latency, all of that setup stuff, all to make sure that she gets the message and she gets the message as I originally intended it to be sent. That's why. All right, back to live action over here. Let me ask you, based on what you've seen so far, are you sad that I can't throw markers at you today? No. Let me ask you, based on what you've seen so far, what do you think the Twitch stream you're watching right now is using at layer 4 if you were sniffing in a Wireshark? And it's not just Twitch, it's YouTube, it's any type of one of these sites that you're going to be watching streams from. You know the way I asked it, the answer is not UDP. It's actually TCP. When you stream from these sites, you're actually not streaming live. The bits and bytes are downloaded reliably to your machine, and you're technically, Netflix works the same way, you're technically streaming from your machine because of a few different constraints that I'll talk about another time. But the main thing is right over here. We still want that reliability when you're doing some live streams. So when I say TCP is guaranteed, 100% guaranteed like death and taxes, that is provided that there's a reliable connection. For instance, if John Bauer is at home and his power goes out, it's not guaranteed. John Bauer is not a transmitter or a transformer. He's a cool guy, but he is not supplying the power for a network infrastructure. So up until 15, 20 minutes ago, the way my spiel went, oh yeah, TCP is always guaranteed, just like death and taxes. From this point forward, in all of my classes and all of my presentations and all my demos, I'm going to say TCP is 100% guaranteed, just like death and taxes, unless the power goes out in John Bauer's house. And I will do that from this point going forward. All right. Thank you for your patience and attention. And please feel free to connect with me on LinkedIn, follow me on Twitter, follow me on Instagram. It's been a pleasure. If you have any questions on anything I said, feel free to send me a message and get in touch at any point in time. Weissman out.